covers the lowest common ancestor algorithm using the Euler Tour technique and some properties of this algorithm. Let's start with the motivation problem. Problem statement is like so. Given a rooted tree, we're given a rooted tree consisting of n nodes and n minus 1 edges. For example, this would be one example, rooted at 1 with 8 edges and 8 nodes and 7 edges. Also, we're given m queries of the following. We want to compute the shortest path, or the distance, from any node A to any node B for finding the shortest path between node A and node B. So for example, if we're given this tree rooted at 1 with 7 nodes and 6 edges, we want to find the distance from node 4 to node 3. So those are these two nodes over here. And the shortest path is highlighted in red, and the path is of length 3. So our answer to a certain query of dist 4 and 3 would be 3. Now to implement this, each query would have to take order of n time because we would have to iterate over the graph using any search algorithm like BFS or DFS. And finally, we would have to do this for all m queries. That would finally give us an O of nm time. This is slow because, for example, if we had a million nodes and a million queries, O of nm will become quite slow. So how do we optimize this? A slight optimization to the algorithm includes pre-computing the distance for all AB, so all pairs A from any node A to any node B, before answering queries in order of 1 time. So for example, if we're given this graph, we want to compute the distances for all AB. So this includes 1 to 2, 2 to 4, 2 to 3, any node to any other node. It's 3 to 7, so there are n squared pairs, and this is why it's an optimization. For example, if we were given 3 queries to compute the distance from 1 to 2, the distance from 3 to 4, and the distance from 1 to 2, we would be computing these two twice. Even though we computed the previous one once, we would be computing it again, and that is a problem. So finally, this optimization will give us order of n squared plus m time, which is slightly better than the O of nm time. Now we bring in the concept of lowest common ancestor here, and later on we will be tying it back to the original problem statement. So the lowest common ancestor of two nodes given a certain tree is defined as the following. For example, if we're given nodes U and nodes V, marked in red, each node has its own ancestor path. So for example, this node, its ancestor path is the path from this node all the way to the root. So that path includes this node, and this node. So that's the ancestor path for this node U. For this node V, the ancestor path includes these nodes. Now, we're looking for the lowest common ancestor. So let's focus on common ancestors. So these 3 nodes are ancestors of this node, and these 3 nodes are ancestors of these nodes. Now, when we're looking at common ancestor, it means that node exists on both of the ancestor paths for U and V. So, for example, the root exists on both ancestor paths for this node and this node. Also, this yellow node over here exists on both ancestor paths. Now we're looking for the lowest common ancestor. So both of these nodes are common ancestors. However, this node exists lower than this node when we look at the tree like this. So that is the lowest common ancestor of given node U and V. Now we look at a slightly different example. It works differently. So for example, during the LCA of U and V, if one node is the ancestor of the other node, it is considered as the lowest common ancestor of both nodes. So example, this node is actually on the ancestor path of this node. In that case, this node would actually become the lowest common ancestor of both nodes. So one thing we need to remember is a node can be an ancestor itself, and this node exists on the ancestor path of this node. So these two nodes, this node actually is the lowest common ancestor of this node. We cannot include this node as a lowest common ancestor because it is only an ancestor for one of the nodes. For the other node, it's actually a child. So that's an example of one unique LCA query. Now, for the algorithm for finding lowest common ancestor given two nodes, starts with something called the Euler's Tour. So the algorithm starts with a sequence consisting of the Euler's Tour given the tree. And that works like the following. We visit all the nodes in DFS order, just like how a normal DFS would visit its nodes. However, While backtracking to ancestors, including parents and grandparents, we consider to be revisiting them. For example, the tree over here would give us such a tour, 1, 2, 1, 3, 4. So how it works is, let's say we start at 1, so we add 1 to the tour, head on to 2, as normal DFS would do, add 2 to the tour. However, to go to 3, we would have to backtrack to 1, and we don't just ignore this one, we actually add it to the tour again. So that's why we get 1, 2, 1, 3, 4, 6, 4, 7, and so on. This is just a small portion of the tour. Next, we have observation. This observation is key for finding the lowest common ancestor of two nodes. So in this example, we have nodes 4 and node 8. And we have the tour, which we computed before. So given nodes 4 and 8, the first thing we need to know is where the first 4 exists in the tour. So that 4 exists right over here, and that's one of the nodes we want to find the LCA for. And that 4 is right over here, and the first 8, node 8 in this tour is this node. So here's our 4, and here's the 8. And what we need to know, what we're going to use is the sequence between these two nodes. So we will be using this later on for finding our lowest common ancestor. Next, we introduce a concept called the depth of nodes. So the root always starts at level 1. The children of the root are considered to be level 2 as they are 1 away from the root. So this node 1, which is the root, is level 1. And all the children of the root, which is 2 and 3, are considered to be level 2. The same applies for 2 and 3, 4, 5, and 6, 7. So this is level 3. 4 and 5 are level 3, 6, 7, 8, level 4. So given a node U, any node U, we want to find the level that node exists in. Given node 5, we know that that's level 3, so depth of U would give us 3. Given node 8, we know that that node is in level 4, so the depth of 8 would give us 4. Using this, so before, we computed the sequence between those two nodes in the LCA tour. So that sequence is 6, 4, 7, 4, 3, 5. We write that sequence over here, and each value in the sequence is actually a node in the tree, because that's what we computed in the Euler Tour. So for each node, we want to compute the depth, the level in which that node exists in. For example, node 6 exists in level 4, so we write 4. Node 4 exists in level 3, 1, 2, 3, so we add 3 to the depth. The same applies for all other nodes in our sequence. So if we look at the depths, 4, 3, 4, 3, 2, 3, we want to find the minimum depth between this sequence. That depth is 2. 2 is less than 3 and 4. When we look at what node that depth points to, the lowest depth, that is points to node 3. So now we know the node in red, circled in red, is the lowest common ancestor of node 4 and node 8. Using this, we will be connecting back to our original problem statement with a property of the lowest common ancestor. And now if we look at the depth, what we did was we need to find the minimum depth given a sequence of integers. Now this connects to a different problem called as the range minimum query problem. And we have data structures for that to compute that really quickly. However, these data structures are not included in this video. But if we need to know which one to use, segment tree, and there's two used for, one is segment tree and another one is sparse table. In this implementation, we'll be using sparse table, which queries in order of 1 time to find the minimum depth. A brute force approach would just be to iterate over the depths and to calculate the minimum value. However, LCA, we want to calculate as fast as possible for the original problem, so we're going to use sparse table. Now here's our connection to the problem statement. So we're able to find the LCA of U and V, any U and any V, pretty quickly, and it's working. How do we use this to optimize the original problem, which we were able to optimize to order of n squared plus m? Now given U and V, if we want to find the distance, for example, if U is 4 and V is 8, this happens to be a formula that we can use to find the distance from these two nodes. The first is the depth of U, which is the depth of 4, plus the depth of V, which is 8, minus 2 times the depth of the LCA of U and V, which in this case is 4 and 8. So why does this work? For example, if this is our tree and we wanted to find the distance from 4 to 8, if you look at the first value, that's the depth of u. Let's say u is 8. So the depth of 8 can be drawn as like this, so which is 4, and that's the depth of u, which is 8. Now we're adding the depth of v, which is going to be 4, and we can draw 4 like so. That's 1 to 3 plus the distance from 3 to 4. Now minus 2 times the depth of the LCA of u and v. Now if you look at the LCA of u and v, that is 3. Now if you look at the depth, that actually exists in level 2, so that's 2. In this case, 1. Now we're subtracting that 2 times because in the depth of u, we included that value once, and in the depth of v, we included that value once. Why does this give us the distance between the two nodes? That's because, well, if you look at the distance between 4 to 8, that equals this bit over here plus this bit over here. So these values exist somewhere between these numbers. So how do we arrive at the value of this and the value of this? So when you look at the value for 8, we added everything from the root to the 8. So we need to subtract something. And what we're subtracting happens to be the depth from 1, which is the root, to the LCA of that node, which is 3. Now we're multiplying by 2 because the same applies to node 4 and its path. 1 to 3 to 4, we need to subtract 1 to 3 for the distance from 3 to 4. So we subtract the LCA distance, which is 1 to 3, and that's why we get the distance from 4 to 8. So we can use this original problem to compute any query. So using sparse table with n log n build time and order of 1 query, any data structure for the range minimum query problem, and an order of n initial DFS time for computing the Euler's Tour and the depth of the nodes, final time complexity for m queries will be order of n log n plus m, significantly faster than the pre-processing technique, which we had to calculate for all pairs of a and b. So this is why this is much faster technique for the original problem. So in this video, we covered the BFS optimization problem for motivation to why we would use the lowest common ancestor between two nodes and why we would use the Euler's Tour technique. And we explained the BFS pre-processing optimization, make our code a little bit faster. Then we talked about the LCA algorithm using Euler's Tour and range minimum query to compute the LCA of any two nodes. And we applied that algorithm to the original problem for a significantly faster solution.